Hello and welcome to Lecture 9 on improper integrals. So up until now, until Lecture 8, we've been dealing with integrals that either don't have any bounds at all, and we call those indefinite integrals, or we've had definite integrals, but the bounds from a to b have been finite. So in this video, we're going to introduce one type of improper integral where your bounds can be infinite. So either the upper, the lower, or both bounds could be infinite. And that's called a type 1 a type 1 improper integral. So we're going to deal with those in the first part of the video, and then we're going to show you what type 2 improper integrals look like. So we start with a rather long definition. I'm just going to fill this in as we go. We have to get the notation out of the way first before we start doing problems. So say you have some integral from a to t. A is some fixed constant, real number. Let's say that this exists for every t that's greater than a forever. So then the way you define the integral from a to infinity is you go back to calculus 1 and you look at the limit. So we're going to look at the limit as t goes to infinity of the integral from a to t of f of x dx. And then very similarly, if your lower bound is the bound that's going off to infinity, so that would be negative infinity, it would go off to the left forever, then this would be the limit as t goes to negative infinity of t to b f of x dx. And then we say that either one of these integrals, these improper integrals, are convergent if the limit exists. And for us, what I mean by that is a finite number. And then otherwise, it is divergent. So what you need to know is that a convergent integral will be calculated as an existing finite number. And then if you have a divergent improper integral here, then that means it'll go to some kind of infinity, like plus or minus infinity. Or it just won't settle on a particular finite number. So then the way you define the case where both of the bounds are infinite, this is like the most extreme case, is you need to look at each of case A and B separately. And then the way you look at this one is if you say, okay, well, if each of them exists separately, you would choose some real number, A. It doesn't really matter which one it is. And then we would split these up into the integral from negative infinity to a of f of x dx plus the integral from a to infinity of f of x dx, where you would go back to the definitions here to figure out what each of these are separately. And if both of these are convergent, and they both must be convergent, then that's what the integral from negative infinity to infinity equals. So let's take a look at this first example right here. So notice that this is actually case A from over there. And what I mean by that is that it's the upper bound that's going to infinity. So that falls under case A. So the way I write this using the definition is I say this is equal to the limit as t goes to infinity. So I'm just reading this over here. And then A this time is 1. And it goes from 1 to t. And my f of x is ln of x times 1 over x cubed dx. So there's a reason I wrote it like this. Off to the side, what I'm going to do is I'm going to just do the indefinite integral for this, and I'll plug it back in when I'm done. So off to the side, I'm going to do some scratch work. I'm going to do the integral of ln of x times 1 over x cubed. So here I have the integral of two very distinct or different families of functions. And what integration technique to use for this? By now, you should recognize that this is integration by parts. And we always pick ln to be u. That's usually our very first choice. So for u, I'm going to choose ln. And for dv, I'm going to choose 1 over x cubed dx. So if I take the derivative of u, I get 1 over x. And the integral of this, if I go backwards, it's negative 1 over 2x squared. If you don't believe me, just take a second and check that. Do the derivative of this, and you'll get this. So for integration by parts, I do my plus and my minus symbol. And then this integral is equal to the first diagonal multiplied together, which is negative 1 over 2x squared ln x. And then I need to multiply these two together, and this will remain in the integral because I have a row right here. This is du, and this is v. So a negative times a negative is a positive. My 1/2 will be factored out front, and I get 1 over x cubed. But then I can integrate that. That's just going to be what I had just before. This is 1/2, and then the integral of that was negative 1 over 2 x squared plus c. So what I've done off to the side is I've done the indefinite integral first. And now I'm going to plug in my work over here. So this is equal to the limit as t goes to infinity. And then this integral right here, I just calculated that. So that's going to be negative 1 over 2x squared ln of x, and then minus 1 over 4 x squared. And that's me simplifying this part right here. I don't need the plus c anymore because I'm going to evaluate this from 1 to t, just like that. So I'm going to plug this in. This is equal to the limit as t goes to infinity. I'm going to plug in my t. I get negative 1 over t squared ln of t minus 1 over 4t squared, and then minus, and you plug in 1 now. So if you plug in 1 for ln, you get 0. If you plug in 1 here, you get 1/4. So we have to figure out what this limit is. Well, what happens, I'm going to start with the second term here because I think that's the easiest to explain. I have a fixed constant over, and then this is going to infinity. So from calculus 1, our first unit on limits, this goes to 0. 1 over a huge number goes to 0. This, I have ln over t squared. And which one of these things grows faster? Well, actually, t squared grows much faster. So this double less than symbol here means that t squared grows much faster. So one way you could think of this is that this function's bottom heavy. So the denominator is growing much faster. So this is also going to go to 0. Another way you can see that is you could use L'Hopital's rule. This is infinity over infinity. So go back to L'Hopital's rule, and you can show that this goes to 0 as well. OK? So there's two different options for you. Well, everything's 0, right, except for this. I have negative, negative. This is 1/4. So let's use some vocabulary. This integral is convergent because its value is a finite number, a single finite number. It's 1/4, so it's convergent. All right, let's take a look at the more interesting case here. So we have an integral, and the bounds are both infinite. So now we're in case C. So what we need to do is we need to check if individually both the left and the right one are convergent. And we can pick any a value that we want, any a that's going to link these together. So, excuse me. So let's just choose a equals 0 because it's convenient. I think that's an easy number. Off to the side again, I'm going to do my scratch work. So what's the indefinite integral of this? Well, this is actually an easier technique than this, at least in my mind. This is a u sub, right? If you let u equal the denominator, then du is 2x dx. So that means 1/2 du is x dx. And if I substitute that in here, I'm going to get the integral of 1 over u, and there's this 1/2 out front. So this u is here, and the x dx substituted out for 1/2 du. I'm hoping you're getting very comfortable with your u sub by now. So then this is equal to the ln 1/2 ln absolute value of u plus c, but then my u is just 1 plus x squared. And 1 plus x squared is a positive number, like for sure, no matter what x value I plug in. So I don't even need these absolute value bars anymore. I can just call these parentheses like that. So this is kind of my scratch work for what to plug in for here. Now, because they're both infinite, we need to consider both cases. And if either one of them are not convergent or divergent, then we immediately say that the starting integral is divergent. So the first one I'm going to start with is I'm going to take a look at the left one, or the left one being the lower bound goes off to negative infinity. So what is this integral defined to be? Well, here I would go to case 2. This is a case, or I keep calling them numbers. This is case B, right, where the lower one goes to negative infinity. So what's this? It's the limit as t goes to negative infinity of t to 0 x plus 1 over x squared dx, okay? And then this is the limit as t goes to negative infinity. This integral right here, I calculated it. It's this. So I'm just going to fill it in. The 1/2, bring it out front because it's a constant. So out front means out front from the limit. And then I have ln of 1 plus x squared. The plus c is not necessary anymore because now I'm doing a proper integral. It's going to go 0 to t like this. So this is 1/2 limit as t goes to negative infinity. If you plug in 0 for x, ln of 1, just like the other problem, was 0. So this is 0. And I'm going to plug in t, so minus t, or minus ln 1 plus t squared. Now what happens to this? So you're plugging in an extremely huge negative number into t squared. So this is actually going to ln of positive infinity, right? ln of positive infinity, because the square will make this positive. So what happens to ln? It is crucial that you know the graph of ln, by the way. Like, it's very crucial moving forward. So this is your opportunity to review the graph of ln. As we go off to infinity, because this approaching negative infinity for this means ln is going to infinity for its argument, this goes to infinity. So the answer to this is I have 1/2 times, and I get minus infinity. Well, minus infinity is not a finite real number. So this means we have a divergent integral. So this is divergent, but that automatically means that the original integral is also divergent. So we don't actually even have to check the second case where you go from 0 to infinity. You don't have to do both of them. As soon as one of them became divergent, we're done. So the answer to this one's divergent. All right. Our last example is a little more abstract. So it says, for what values of p, so p is some constant, will this integral, so this is a case A integral from 1 to infinity of 1 over x to the p converge. So I want this to be a finite number. I want the limit to be finite for this. And this is called a p integral, where you have 1 over x to some power of p. So as an example, if I had the integral from 1 to infinity of 1 over x squared, that's called a p integral. So it just looks like this. So here p is 2. Will this converge? Well, how do I know if something converges? I need to make sure this is finite. So let's go ahead and integrate this. So this is equal to the limit as t goes to infinity, integral, the integral from 1 to t, not infinity, 1 to t, of x to the negative p dx. So I just brought the whole term up. And now I'm going to do the backwards power rule. So this is the limit as t goes to infinity. I'm going to add 1 to the power, so negative p plus 1. I'm going to divide by the new power, which is negative p plus 1. And then I'm going to plug in t, and I'm going to plug in 1. So this is the limit as t goes to infinity. Plug in t, you get x minus t plus 1. Oh, I'm plugging it in the wrong spot. Plug it in for x, and you get t to the negative p plus 1 over negative p plus 1 minus, and if you plug in 1 for x, you get 1 to any power is just going to be 1 minus p plus 1. And what I want to know is, when is this going to be finite? So if you have t going to infinity, and this infinity is sitting in the numerator, this is going to blow up to infinity. However, if you consider what happened back here, for example, I had 1 over infinity and it went to 0. That's where I want the infinity to kind of be. I want this t to be in the denominator when I'm done. So the question is, how do I ensure that t is going to be in the denominator? So when I take it to infinity, this will remain finite. I need this to be a particular number. So we need negative p plus 1. This right here needs to be less than 0. You need the power to be negative. Overall, that needs to be negative. So then t will go to the denominator. So if you want this to be negative, this needs to be less than 0. OK, well, solving that, I get p needs to be greater than 1. So whenever you have p is greater than 1, when it's in this situation, we will have a convergent integral. So let's do my example here. Here p is 2. So as long as p is greater than 1, we are convergent. So then I should say, if p is less than or equal to 1, this integral, 1 over x to the p, it's divergent. So in an example of that would be the integral from 1 to infinity of 1 over the square root of x. Because here that would be the integral of 1 over x to the 1/2. And 1/2 is less than p. So this would be divergent. OK, so that wraps up our first part of the video on type 1 improper integrals. And then in the next part of the video, we're just going to talk about type 2 indefinite integrals. Or sorry, improper integrals. I'll see you in just a moment for that. Hello, everybody, and welcome back. So in this part of the video, we're going to talk about type 2 improper integrals. And these are integrals where on the bounds of integration from a to b, you have a discontinuity for the function you're integrating over. So we have an integral from a to b. These aren't necessarily some type of infinity, but f of x is not a continuous function. And we have several cases here, just like I did in the previous part of this video. So case 1 is where you are continuous from a to b, except for at b, at the very right endpoint. Then the way you define this is just like we did before with limits. So you have the limit as t goes to b on the left, because we're approaching the very far right number on the interval, the endpoint on the right. So we're going to approach that from the left where we're still continuous. This is the integral from a to t of f of x dx. And that's true if it exists, just like before. If we have that the limit actually exists as a single finite number. Here we have f is continuous, and we kind of just flip it around. So now it's the left endpoint where we're not continuous, but everything else we're continuous. So for this one, you have the limit as t approaches a on the right, the integral from t to b of f of x dx. And again, that's true if this limit actually exists. Sometimes it will, sometimes it won't. And then finally, if we have a case where the point of discontinuity is somewhere in between those two numbers, so some c between the left and the right endpoint, then we can define this and find its value as long as both of these integrals converge. So if these both converge based on the two definitions up here, then the way you find this is you have the integral from a to c f of x dx plus the integral from c to b of f of x dx. And the way you find these two is you would go back to these two cases here. OK, let's take a look at some examples. So here we have the function we're integrating over. This is f of x equals 1 over the square root of x minus 2. And in other words, that's x minus 2 to the negative 1/2 power, if I wanted to rewrite that. But I think it's more helpful to look at this one. There is a particular x value where we are not continuous. So f of x is not continuous at x equals 2. And that's a problem because that's the left endpoint. This is like my A and this is my B from over here. So if you look at what we have this left one, we're not continuous. And that case is right over here. This is case B. So if I want to do something similar to what I was doing last time, if that made sense for you guys, I'll just do it again. This is the second case right here. So what we need to actually do is we need to look at the limit as, and I'm going to say t approaches 2 on the right. So I'm in this second case, 2 on the right. Integral from t to 5, that's my b, of x minus 2 to the negative 1/2 dx. OK, let's go ahead and integrate that. That's just the power rule backwards. We're not even going to get anything to account for the chain rule in here. So this is the limit as t goes to 2 from the right. Integral of this, add 1 to the power. It's going to be positive 1/2. And then I need to divide by the new power. So if I divide by the half, that's the same thing as putting 2 here. And then from here, what I'm going to do is I'm going to plug in 5, and I'm going to plug in t. So that's how I integrate that function right there. And then what I need to do is I need to go ahead and plug that in. So I'm going to get the limit as t goes to 2 from the right. Plug in 5, we get 2 rad 3. And if you plug in t, you're going to get 2t minus 2 times t minus 2 to the 1/2. And now we have to evaluate this limit. So what happens if you plug in 2 into this limit? So we'll just do the direct substitution. If you plug in 2, we get 2 root 3. And if you plug in 2, you get 2 times 0 is 0. So this converges. We get a limit that exists. We get a finite number. That's probably the best case scenario, is we get that this actually converges. Let's take a look at this one. So this time, I'll kind of section this off. This time, the function is 1 over x minus 1. And where does this have a problem? Take note of the interval. First, we need to figure out if there actually is a problem here. So there is a problem. F of x is discontinuous at which x value? It's at x equals 1. And 1 is strictly between 0 and 3. So we're actually in the last case right here. This is case C, where we have a discontinuity that's like directly in the middle of the two bounds that we're given. So what we need to do is we need to look at both of these separately. And the C this time is going to be 1. So let's go ahead and take a look at the one that's kind of on the left side. So we need to look at the integral from 0 to 1, that spot where we're discontinuous at. So from 0 to 1 of dx over x minus 1. We need to look at this. This right here, where we're discontinuous at the upper bound here, that's case A, right? This is case C, and this is case A. So what happens when we're discontinuous at the upper bound? What do? We do something like this. We say, well, we have the limit as t goes to 1. This time, it's going to be 1. From the left, integral from 0 to t of dx over x minus 1. And now let's go ahead and take the integral of this. I get the limit as t goes to 1 on the left. 1 over x to the first power, we learned that rule from the previous videos. That's ln of whatever's there. And I need to evaluate that from t to 0. So this is the limit as t goes to 1 on the left, or from the left. Plug in t, I get ln of t minus 1 minus ln of 0 minus 1, absolute value is 1. So this just goes to 0. And then this is what I'm focusing on right here. So this is the limit as t approaches 1 from the left of ln of t minus 1. We need to really take a look at that. So again, knowing your ln graph is super important. This will be ln of t. So what happens if you get very, very close to 1? Well, if you plug in 1 and you get very close to it, this gets very close to what number? This goes to 0. And the absolute value bars keep it positive. So we're always going to be just slightly larger than 0 the whole time we're getting closer to 0. So you can think of us as moving down the graph here. Where do we go to eventually as we approach 0? We actually approach negative infinity. So that means that this diverges. And by this, I mean this integral from 0 to 1 diverges. But as soon as one of these two things diverges, the entire thing diverges. So now I know automatically, I don't have to check the other one, that the original also diverges. And it's as easy as that once you find one of them that doesn't work. OK, the last thing I need to talk about in this section is something called the comparison test for improper integrals. So I'm going to go ahead and write out the statement of that. So suppose f and g are continuous functions. So they're continuous. And it's such that f of x is always larger, or at least as large as g of x. And they're both above the x-axis the whole time. So we have that this is true. For all x greater than some a, we'll just say some constant value. Then there's two things that you will know for sure. So if you know that the integral from a to infinity of f of x is convergent, then this lets you know that the integral from a to infinity of g of x is convergent as well. So this is kind of a theorem that lets you know what happens in relation to the other one based on which one is larger than the other one. So here, if you're a convergent object, that means your limit goes to a finite number. OK? So if I know something is finite, and then I have a function that's strictly smaller than something that's finite, if you're smaller than a finite number, then this one's also got to be finite, right? And being finite, the limit converging to something means you're going to something finite. So that's why if something's convergent, anything smaller than it is going to converge. Now we could flip that around, just flip it on its head, and we could say the following thing. And you could probably already guess what I'm going to say. Let's talk about divergence. So if the integral from a to infinity of the smaller one, g of x dx, if that one diverges, i.e. if it's already too big, then the integral from a to infinity of the larger one, if you're larger than something that's already too large, you're too large. So then this is divergent as well. So these are the two comparisons that you get for free. You have to know something either is convergent to start or divergent. And then if you're smaller than a convergent, you're convergent. If you're larger than a divergent, you're divergent. All right, hopefully my reasoning there makes sense. This last example asks you to explain why this integral is divergent. And what I'm going to do is I'm going to start with this right here. Recall that the integral from 1 to infinity of 1 over x is, and remember, this is our special type of integral from the other part of this video. This is called a p integral. Is this convergent or divergent? It's divergent because p equals 1. It's the p integral. Remember, you have to be less, or you have to be greater than 1. P has to be greater than 1 for that to converge. So we know that this is a divergent thing. Also, 1 over x is less than 1 over e to the negative x over x, because e to the negative x is always positive for any real number. So I haven't changed the denominators. If you add something that's positive to the numerator, you make a larger fraction. So this is certainly bigger than this. And this is my g of x, and this is my f of x from the theorem here. So then I can say, so therefore, by the comparison theorem, so the comparison test for improper integrals, the original integral I'm interested in, this one, 1 to infinity of 1 plus e to the negative x over x, is also divergent. So the way you do comparisons, and you're going to see this later when we do series as well, is you start with something you know for sure is convergent or divergent, and then you make the appropriate comparison. So if I started with something that's divergent, I better supply something that is even bigger to show that that's also divergent. And that's what I did right here. All right. Thank you so much for watching this video. In the next lecture, we're going to wrap up all of our integration techniques. So I will see you then. Have a nice day.